As we venture into the next reaction, which is elimination, those products will be alkenes, among other things. But we'll form alkenes as our organic product. So we should take a minute and do a little discussion here of the structure of an alkene, and also we should learn how to name it too. So the bond dissociation energies of alkenes. So we have a carbon-carbon double bond. To break that double bond, it's 146 kcals per mole. Breaking that carbon-carbon single bond is 83 kcals per mole, which means that to break the pi bond is 63 kcals per mole. Because remember, a pi bond has, or a double bond, I should say, has an overlap of a p orbital and a sigma bond. So that's what it requires to break just that pi bond, right? Now, because of that, it's more reactive and easier to break because it has less energy, right, for your at least BDE as compared to your carbon-carbon single bond. Now, we have seen the orbital description of the pi bond before. We know that it has this overlap of our p orbitals. So if we take it and kind of rotate it on its side, like we do here, we can see we have this constructive overlap up here, giving you your positive lobe, and down here that gives you your negative lobe. Often what we do when we draw these out, right, is we draw them by just putting in lobes like this. And then we show the overlap by just connecting them like this. Right? So that's your pi bond. This would be your sigma bond, and this is whatever substituents you have sticking off of those carbon atoms right there in the middle. So we often draw it like this simply because it gets to be time consuming to draw it like that over and over again. Now, of course, here it says half the pi bond is up here and half of the pi bond is down there, right? So this is really an indication of the parts of the pi bond. It's not like a negative 1/2 or anything like that. All right, now we know also that we don't have free rotation about a carbon-carbon bond. It requires 63 kcals per mole to get that rotation. So the cis isomer cannot become trans without either a chemical reaction or sufficient heat to overcome that activation energy barrier. The nomenclature of alkenes follows that of alkanes in many ways. So it's fairly straightforward to go through. What we're going to do is we're going to find the longest carbon chain which contains the double bond. So when we look at the structure up above, that is the longest carbon chain that has the double bond. We're going to count that number of carbons in the chain, and we're going to determine the parent name or the stem name and add the suffix "ene." So they're alkenes. So let's count them up. 1, 2, 3, 4, 5. So it's a pent, and then it's an ene, right? Because we have a carbon-carbon double bond on it. Now we want to number, looking at this next one, we've just done these two. We want to number the carbon chain starting from the end closest to the double bond. And for cyclic compounds, the double bond must start at carbon number 1. So we've numbered it correctly up here above. Next, we want to indicate the position of the double bond by adding the number of the first carbon of the double bond in front of the alkene name. So this would be 1-pentene. The other way we could name this is we could call this a pent 1-ene. Both are acceptable. Okay. Next, we add substituent names. So I think we all know pretty easily that that's a methyl. So then putting that all together, this is simply a 2-methyl, and we could call it a pent 1-ene. Or we could call it a 2-methyl 1-pentene. Either are acceptable. There's an advantage to the numbering and the suffix here that we'll see later on when we get more than one functional group on a molecule. So if you have a double bond, for example, and an alcohol, they're called ene-all. So putting the numbers on the end is helpful because it gives you a location of the double bond and the alcohol. Now this next one is we need to indicate stereochemistry, that double bond, when applicable. And you remember before talking about cis and trans. And what we need to learn in a minute is this EZ system. So sometimes cis and trans is not applicable even though we have geometric isomerism. So we'll talk about that down below. There are some special groups that we need to memorize. So if we have a CH2 and a CH2, IUPAC name of that is ethene. However, most chemists will call this ethylene. And if we have a CH3, CH, CH2, IUPAC of that is propene, but most chemists will call this propylene. A couple other groups here too. If we have a CH3, we know from previous chapters that that's a methyl. A CH2 group is called a methylene group. This group is called an ethenyl group, and then an allyl group is this guy right here. The EZ system for alkene nomenclature is fairly straightforward. Let's take a look at a couple examples down here below. Remember, to name a molecule as being cis or trans, we need to have two identical groups, one on each carbon. And so we always took our carbon-carbon double bond and we kind of divided it into these two halves, just like so. Right? And in this case, of course, the H's would be the identical groups, and this would be cis. Okay. Looking at the next two structures, though, can we name these as being cis or trans? Well, there's four different groups here. So we can't use the term cis, we can't use the term trans. However, do these exhibit geometric isomerism? Well, they do. Remember, to test to see if we have stereoisomers, or if the molecules are identical, we can superimpose them on top of each other. And we can see from these two structures that if we put the first and the second molecule on top of each other, that the methyls would match up, the H's would match up, that carbon would match up right there, right? This carbon would match up here, but our iodo group and the chloro group would not match up. So these two structures are different from each other. And if they're different from each other, we need to come up with a name that indicates whether or not the iodo group, for example, is up here or whether or not it's down there. So the system that we're going to use here is called the EZ system. I usually tell students it's easy. It's not that hard, actually. So what we're going to do is this. There's three basic rules to this. So we're going to prioritize those four groups attached to the carbon-carbon double bond using RS priority rules. So those rules, if you remember, are atomic number. Then we identify the higher priority group, right, on each of the carbon's double bonds, and we compare the relative positions of those groups to each other. One of two things will occur. If they're aligned on the same side of the double bond, then we call it the Z stereoisomer. And Z stands for zusammen. And I apologize for all the German-speaking students that are out there. But in my mind, this always sounds like zusammen. Zusammen side. They're on the same side. So it's silly, but that's how I remembered it from when I took organic chemistry. If they're on opposite sides, then they're called the E stereoisomer. So we have the Z or we have the E. And if we look at those examples from before, let's see if we can name them as being E or Z. So looking at this structure here, let's take our two halves. So this is half number one. This is the second part here, number two. And what we're going to do is we're going to look at this carbon and that carbon, and they each have two substituents. And one of them will be numbered 1 and one of them will be numbered 2. So we're not doing 1, 2, 3, 4 like we did with like a R and S. We're just looking at the atoms that are on the carbon that are in this little box here. So H is going to be number 2 and the carbon is number 1. What about the other side? Well, what has the higher atomic number? Iodine or chlorine? It's iodine. That's number 1, and then this is number 2. So when we look across this double bond, the two number 1 groups are on the same side. So this is going to be Z. Right? Now putting the full name of this thing together, let's see if we can name it. Here we have 1, 2, 3 carbons, so it's propene, right? Or 1 propene. So we'll name it over here on the side. So prop 1ene. And then staking off of carbon number 1 here, because we number from this side, because we want that number to be 1, we have a chloro and an iodo. So it's a 1 chloro, 1 iodo, prop 1ene. And we're not totally done yet because we need to squeeze in here the fact that that is a Z. So it kind of got crammed in there, but you get the idea. All right, so that's Z. The other isomer over here would be the E isomer. So this would be E, 1 chloro, 1 iodo, prop 1ene. And we could also call this 1 propene too. All right, let's see if we can name this beast that's down here. So first thing to do here is to find the longest carbon chain. Well, that's pretty clear. So here's our longest carbon chain. Is this guy. All right, so what side do we number from? Well, we want to number from over here. That gives us a 1, a 2. It puts our double bond at the lowest possible number. So 1, 2, 3, 4, 5, 6, 7, 8. So it's an oct. Now we have double bonds at position 2 and position 5. So that's the start of a double bond. That's another one. So it's a 2, 5. And when we have 2, we call them dienes. Right? So it's an octadiene. So we need to throw an A in there. So we have a 3 and a 7 dichloro and then a 4 methyl. Now we just got to put this big mess together. So this is going to be a 3, 7 dichloro, 4 methyl. So we took care of those two guys. And then we could do it this way. We could do a 2, 5 octadiene, or you could call this an octa 2, 5 diene. Now we're not done yet though. So we have stereochemistry left to deal with. We have two issues here. We have double bonds and we have stereocenters that are R and S. So when we look across this double bond right here, right, this is your number 1. This methyl up here is number 1, and that chloro would be your number 1. So they're on the same side. So this is going to be a 2. Let's just put it all in right here. This is a 2, in that case, a Z. So we taking care of that. Let's come down here. So that's 1, 2, 3. This is 4. So now we're going to deal with 4 over here. What do we have staking off of here? There's an H. That H is number 4. This side's number 1. This side's number 2. That's number 3. So we're moving around that direction. That is the R direction. But look, H is pointing at us. So we have to change our R to S. So that's a 4S. All right, looking over here at number 5. So we have H's here. H's are opposite. Opposite is E. So that's a 5E. And then lastly, what about this guy here? Well, that H is 4. Chloro is 1. This side is 2. That's 3. So we're moving around that direction. That is R. And then H is pointing away, so we're good. So that is a 7R. All right, so the full name of this thing is 2Z, 4S, 5E, 7R, 3,7 dichloro, 4 methyl, 2,5 octadiene.